Let's look at our first conic section, the parabola. We've defined parabolas before, but this will be a geometric definition. A parabola is the collection of points P in the plane that are the same distance d from a fixed point F as they are from a fixed line D. A picture helps explain this definition better. Here I've oriented the parabola arbitrarily, so it doesn't matter if it's facing up, sideways, so I did it kind of kitty corner. In the center of the curve of the parabola is a point we're calling F. The distance from F to P is the same as the distance from P to this line D. So these two yellow lines are the same length. And this is true for any other point on the parabola as well. So as the parabola goes outward, we can pick a different point, and the distance from P2 to F is the same as the distance from P2 to this line, which we're calling D. So if I pick the vertex on the parabola, the distance from the vertex to the focus is the same as the distance from the vertex to the line D, which is called the directrix. The focus is always inside of the parabola in the hug of the curve, and the directrix is always behind the vertex. The imaginary line that bisects the parabola is called the axis of symmetry, and it will go through the vertex and the focus. If we draw a line from one side of the parabola to the other through the focus, we call that line the latus rectum. The length of the latus rectum is 4a units long. We'll work on defining that a little bit more in a minute. Let's see if we can derive the equation of a parabola. Let's go ahead and just fix our parabola so that the vertex is at the origin and that this parabola opens facing right. So that means our focus is on the x-axis, and again, our vertex is here at the point 0, 0. We can go ahead and draw our directrix, which is the line beyond the vertex, the same distance from the vertex as the vertex is from the focus. And we'll go ahead and define that distance to be arbitrary. Even though it kind of looks like it's about 3 units, we're going to go ahead and just say that it's a units. So the focus is at the point a0, which makes the directrix the line x equals negative a. So in other words, the directrix crosses the x-axis at the point negative a0. If we pick an arbitrary point on this parabola, let's call this point x, y, the distance from the focus to that point is the same as from that point to the directrix. Now, I know my picture doesn't look like it. That's because I drew this freehand, but this line right here is the same length as this line right here. So as an equation, the distance from the focus to that point is equal to the distance from that point to the directrix. So if we want to go ahead and calculate the distance from the focus to that point, remember the point's coordinates are x and y, and then the coordinates of the focus are a and 0. So applying the distance formula here, we have x, so this x minus a squared plus this y minus 0 squared. So we've calculated the distance from the focus to this arbitrary point. So now we'll go ahead and clean it up just a bit. Y minus 0 is just y, so you just have a y squared here, right? So now we want to focus on finding the distance from the directrix to that point P. So the directrix we know is a units from the y-axis because it's the line x equals negative a. And we know that the point P is x units from the y-axis. So x plus a is the distance from the point P to the directrix. Now we go ahead and square both sides of the equation so that we can get rid of the square root on the left, and we're going to square those absolute values, and so it just turns into squaring x plus a as a polynomial. Go ahead and clean up the equation by subtracting a squared and x squared from both sides, and then we'll go ahead and add 2ax to both sides of the equation so that we're left with y squared equals 4ax as our equation for this parabola opening right. So here's the definition. The equation of a parabola with vertex 0, 0, focus a 0, and directrix x equals negative a is y squared equals 4ax. And so this is our general picture of that situation. This is in implicit form because it is not solved for y. Of course, we could take the square root to get y by itself, but we actually leave it like this for conic sections. So now that we have a basic equation to use here, let's go ahead and put it to use. Find the equation of the parabola given the focus of 4, 0 and the vertex of 0, 0. I highly recommend drawing these pictures just so you can see the orientation of the parabolas. So since the vertex is at 0, 0 and the focus is at 4, 0, I know that I'm going to make this parabola open to the right. And then my directrix is going to be at x equals negative 4 back here. And it looks like my graph's off just a little bit, but pretend this is negative 4 and pretend this is 4. So I know that the distance from the vertex to the focus is 4 units. And so that is my a value. And so I'll go ahead and replace that a with 4 in the formal formula or definition of a parabola opening to the right. And so my equation is y squared equals 16x. And since the length, since a is equal to 4, then we know the length of the latus rectum is 16 units. So that means that we have 8 units on this side and 8 units on this side. Again, this picture is not really drawn to scale. If we were going to draw it to scale, it would look a little bit more like this. It would be quite a bit bigger. Again, I'm just a little bit off here on the x-axis, but this is a more accurate depiction of what 16 units would look like. So not obviously all parabolas open to the right. We've defined the equation for a parabola who does open to the right and then obviously has a vertex at the origin. So we know the focus of that parabola is a0, the directrix is x equals negative a, and the equation is y squared equals 4ax. Well, how does this equation change if we decide to open the parabola to the left? So now our focus is on the negative x-axis and our directrix is on the positive x-axis over here. And so our focus is point negative a0 and our directrix is the equation x equals a, and our equation becomes y squared equals negative 4ax. We have two other orientations for parabolas besides left and right. Our parabolas can also open up and down. Starting off with a parabola that opens up, again with the vertex at 0, 0. Now our focus is going to be on the y-axis instead of the x-axis, and our directrix will no longer be a vertical line, it'll now be a horizontal line. So our focus becomes the point 0a, and our directrix becomes the horizontal line y equals negative a. Again, the distance from the focus to that vertex is still a units, and from that vertex to the directrix is still a units. The equation is x squared equals 4ay, so you can see that the x's and y's switched in these equations. And then if we open our parabola down, our focus is now 0, negative a, our directrix is the positive y equals a line, and our equation becomes x squared equals negative 4ay. Let's go ahead and practice using those different formats. Let's go ahead and analyze the equation of the parabola x squared equals 2y. So first of all, we'll notice that x squared equals 2y is of the form x squared equals 4ay. So that means that 4a is 2 in this equation. So I can solve that equation 4a equals 2 for a, and we see that a is 1/2 or 0.5. So that means the focus is not very far away from the vertex. So I have a tiny little picture here. We have my vertex at 0, 0, and then my focus is just a half a unit away. We could calculate the lattice rectum here. It is 4a units long. So if a is 1/2, the lattice rectum is only 2 units long. And that actually gives us the distance that these 2 points are from each other. So 2 units between these 2 orange points here because they are in line with the focus. And that helps us actually draw the rest of this parabola and kind of how wide it is. So the points that define the lattice rectum are 1, comma 1/2 and -1, comma +1/2. Let's go ahead and try a different type of example. This time we'll find the equation of the parabola. We're given the vertex to be 0, 0, and the axis of symmetry is the y-axis. So we know it either opens up or down. If I plot the point 2, 3, which it contains, I can see that this parabola is going to open up, in fact. So here's 2, 3, and if the axis of symmetry is the y-axis, then I get the point -2, 3 on the graph as well. So we're going to be using the form x squared equals 4ay, and we have a point 2, 3 that we're going to use by plugging it into this equation so that we can solve for a. So by plugging 2 in for x and 3 in for y, I get the equation 4 equals 12a, divide by 12, and we see that a is equal to 1/3. So now my equation becomes x squared equals 4 times 1/3 y, because of a is 1/3. And I solved for a by using the given point 2, 3 that was on my parabola. So then if I multiply 4 times 1/3, I get the equation x squared equals 4/3 y. So the lattice rectum is also 4/3 long because 4 times a is the length of the lattice rectum. So 4 times 1/3 is 4/3. So this distance is 4/3. So that's 2/3 on this side and 2/3 on this side. So we get the points 2/3, comma 1/3 and -2/3, comma 1/3 as the points that define our lattice rectum.